All right, let's jump right into this explainer. Listen, if you've been keeping tabs on the AI space lately, you already know things are moving at lightning speed. But right now, we're looking at a massive structural paradigm shift in AI infrastructure as we head into 2026. We are officially entering what we can confidently call the inference era. So today, we're going to break down exactly how teams are optimizing large language models at scale, pulling directly from the latest industry data. Let's look under the hood. To really get why this shift is happening, we've got to talk about the fundamental economics of deploying these massive language models. So, first up, you have training. Now, training is the highly publicized, astronomically expensive part of building an AI, but ultimately, it's a one-time process. But inference, that's what happens every single time someone sends a prompt and waits for a response. Once a model is actually live in production, inference, not training, becomes this relentless, recurring, dominant expense.
So ask yourself, what do you think is the single biggest cost for AI teams in 2026? If you ask most casual observers where all those massive AI budgets are going, they're probably going to say, oh, they're training massive new models. But for the teams actually running these things at scale, the core story is entirely cost-driven. Inference has officially overtaken training as the biggest line item on the balance sheet. It's an absolutely massive shift in how capital is being deployed across the entire tech sector.
And because that inference bill has become so incredibly enormous, it's completely flipped the priorities of engineering teams. Which brings us to inference optimization. This is essentially the vital set of techniques used to make each of those AI responses cheaper and faster to generate, but crucially, without materially hurting the quality of the output. This isn't just some nice-to-have feature anymore, or a fun side project for a couple of engineers. Because of those massive recurring costs, inference optimization is quite literally the top engineering priority for AI infrastructure teams today. Okay, so how are the pros actually pulling this off? Well, they aren't just relying on one single magic trick. Instead, the current best practice is to stack optimizations across three very distinct layers: the model level, the system level, and the application level. Industry insiders actually call this the stack all three playbook. To really understand how AI responses are getting so fast and so cheap, we need to take a look at what's happening at each one of these three layers. Let's start at the very bottom with the model level. The absolute heavy hitter here is called quantization. Basically, this means taking a model's numeric precision, say its standard 16-bit numbers, and aggressively shrinking them down to 4-bit numbers. Doing this drastically shrinks the memory footprint and speeds up the raw computation. And right alongside quantization, teams are using pruning, which is literally trimming the fat by removing unnecessary parts of the neural network, and distillation, which is kind of like having a master professor train a faster, younger student to perfectly mimic their knowledge. Stepping up to the system level, we hit a major breakthrough called continuous batching. Normally, a GPU processes one user's prompt, finishes it, and then moves on to the next one. But continuous batching dynamically groups incoming requests together on the fly. Think of it like a factory assembly line that is running at absolute maximum capacity, never letting the machine sit idle for even a second. It makes sure GPU utilization stays incredibly high, which drastically improves throughput. Another big one here is paged attention, which is a technique that manages memory way more efficiently. Oh, and while we're still looking at the system level, we have to talk about speculative decoding. It's such a fascinating approach to generating text. Instead of forcing a massive heavy model to generate a response one agonizing token at a time, you use a tiny, lightning-fast draft model to guess several tokens ahead. Then the big heavy model swoops in and verifies those guesses in one single pass. It literally turns a slow sequential process into a highly parallel one, rapidly accelerating the generation speed. Finally, we reach the top of the stack, the application level. This is where developers are doing things like context compression and prompt caching, specifically something called prefix caching. Imagine a chatbot with a massive, complex system prompt telling it how to behave. Something like, "You are a helpful, concise legal assistant." Instead of the AI engine recalculating that exact same prompt for every single user, prefix caching just reuses the computed representation of it. It completely stops the engine from doing redundant math, saving a huge amount of time and compute. Now, why does this whole stack all three playbook matter so much? Just look at this number. When infrastructure teams successfully stack optimizations across the model, system, and application layers, they can cut their overall inference costs by 80% or more. Think about that for a second. We just established that inference is the biggest line item on the budget. Slashing that specific bill by 80%, that's a total game changer for the financial viability of any AI product. But I know exactly what you're probably thinking right now. If we're compressing numbers and cutting corners left and right, aren't we destroying the actual intelligence of the AI?
Well, when you quantize a model, dropping it from a 16-bit float down to an 8-bit or 4-bit integer, it roughly halves the cost. Yet miraculously, it maintains 95 to 99% of the model's original accuracy. You are getting massive, massive savings for an almost imperceptible drop in quality.
And the industry is pushing this even further. One of the real bottlenecks in generating AI responses is something called the KV cache. Think of it as the model's short-term working memory of your specific conversation, so it doesn't have to relearn everything on every turn. Google actually just introduced a technique called TurboQuant that compresses that working memory down to just 3 bits. That's a 6x reduction in memory requirements, and incredibly, they report 0 measured accuracy loss. It is completely crushing that memory bottleneck.
Okay, so practically speaking, how are developers deploying all this stuff? Right now, there are 4 serving engines dominating production, and they each have a specific superpower. You've got VLLM, which is basically the go-to for general production serving. Then there's SGLang, which uses something called radix attention. That makes it the absolute winner for prefix-heavy workloads, like those chatbots with long system props we talked about. TensorT LLM wins on raw throughput once it's compiled, and LM deploy is great for highly efficient resource scaling.
But here's a fun fact about those top tools. Underpinning them is an incredibly important, kind of secret weapon piece of architecture called Flash Attention 3. It's currently the fastest attention kernel available anywhere, and it acts as the underlying speed engine. Because it's so incredibly effective at managing memory and speeding up the math, it's been integrated directly into both VLLM and SGLang to give them those amazing performance characteristics.
All right, zooming back out to the executive level for a second, all of these deep technical optimizations are driving a major strategic mindset shift that is really worth internalizing. Teams are no longer just reaching for the absolute top benchmark model by default. Increasingly, they're choosing models that might be slightly less capable on paper, but are meaningfully faster and cheaper to actually run. At scale, speed and cost are simply outranking those final few points of benchmark accuracy.
So if you want to start optimizing your own inference stack, our sources point to 3 really actionable steps. First, try running a small model locally, maybe using VLLM or SGLang, and compare performance before and after turning on continuous batching. Second, read up on the difference between throughput-optimized and latency-optimized serving, because they require very different tuning choices. And third, analyze your application's token usage. Break it down into system prompt, retrieved context, and user query. That's usually where you'll spot your easiest prefix and caching wins.
I want to leave you with this final provocative thought. We've seen how this entire inference era is defined by the absolute necessity of optimization, right? The compute bill is completely dominating the ROI calculation for every major deployment. So, as you look at your own infrastructure, ask yourself, at scale, is chasing that top benchmark model really worth your compute bill, or is an optimized, slightly smaller model the true key to your success? Thanks so much for joining me on this explainer, and hey, keep optimizing.